This video is about using velocity t-mid in order to calculate the velocity time graph, which is just another way of doing it besides having to draw the tangents. In order to do this, there is a couple of calculations we first have to make. We have our position and our time data already, and now that we have that, we're going to figure out our change in time, or the amount our time changed between each individual second, which obviously is just going to be 1 second. Each second has a change in time of 1 second, and we need to figure out the change in position over that 1 second. And simply, we're just going to subtract the two position values from each other in order to calculate it. So 5 minus 0 is equal to 5. 20 minus 5 is equal to 15. 45 minus 20 is equal to 25. 80 minus 45 is equal to 35. 125 minus 80 is equal to 45. And 180 divided minus 125 is equal to 55. Once we do this, we then need to calculate t-mid. T-mid is simply the time, or the time point, that's halfway between the two times. So the halfway point between 0 and 1 second is equal to 0.5 seconds. The halfway point between 1 and 2 is equal to 1.5 seconds. 2 and 3 is 2.5, 3.5, so on and so forth. The last thing we need to do is calculate our average velocity over that 1 second interval. So between 0 and 1 seconds, there was a time that had passed of 1 second, and there's a displacement of the object of 5 centimeters, so my velocity over that 1 second would be 5 centimeters per second. Simply taking the position divided by the time. Same for that second interval. From 1 second to 2 seconds, my displacement was 15, the time elapsed was 1, and so my average velocity is 15. From 2 to 3 seconds, my average velocity was 25. Again, just taking my displacement, dividing it by my time. 35, 45, and 55. The reason why this is important is because we know from the midpoint theorem that if you have something with constant acceleration, that you know that the instantaneous velocity at the halfway point is going to be equal to the average velocity over the entire thing, or the time interval. Consequently, since from 0 to 1 seconds I had an average velocity of 5, I know that at 0.5 seconds I was also going 5 centimeters per second. Since from 1 to 2 seconds I had an average velocity of 15, I know that at 1.5 seconds I was going 15 centimeters per second. This allows me to make a graph with my independent variable being t-mid and my dependent variable being velocity. So I have that data. Now I need to scale it. I'm doing the exact same thing that I've always done before. Calculating how many boxes I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And figuring out how many data points I have and going from there. I can pretty much make my time down here, and I can make it in seconds, and it's really going to be t-mid if you want to get technical. So you can label it t-mid or time, either way is fine. But this is going to be 0.5, makes this 1, 1.5, 2, 2.5, 3, 3.5, 4. Now that I have that, I can then plot my individual velocities with time. I know that my total velocity goes all the way up to 55. I have about 30 boxes, so I can count by, let's say, twos. So 2, 4, 6, 8, 10. And this is, again, my velocity, and it's going to be in centimeters per second. So now I'm just plotting the graph. At 0.5 seconds, I had a velocity of equal to 5. At 1.5 seconds, I have a velocity equal to 15. At 2.5 seconds, I have a velocity equal to 25. At 3.5 seconds, I had a velocity of equal to 35. At 4.5 seconds, I had a velocity equal to 45. And at 5.5 seconds, I had a velocity equal to 55. I can draw my line of best fit. Use this point to calculate a line of best fit, and then calculate my slope to come up with the final equation of velocity equal to 10 centimeters per second times t. This is just doing the simple slope calculations. And now I have a graph, a velocity time graph, and I have an equation.